Hello APC Mechanics students in Unit 5 Rotation, Class 1 5.1 Torque and Rotational Statics, Part 1. Then let's start Section 1, Rotational Mechanics. In this unit, Unit 5, you are interested in rotational motion. Everything that have been studied that is related to dynamics was more or less restricted to translational motion. You have discussed several stuffs related to rotational motion like kinematics, for example. To complete this picture across dynamics, basically Units 2, 3, and 4, that has been applied to translational motion, few notions should be introduced first. And to do so, we need to identify an analogy for a force in rotational motion as a first step. Then in section 2, torque, tau, then tau is a Greek letter. We spell it as tau, okay. In the following section, we will try to introduce a quantity in analogy with a force, but related to rotational motion. Now, analogy means comparison. Consider a door that can rotate around a fixed axis along its left side. So this is the door, and the door can rotate in the plane of this axis, left and right. From a top view, the door looks like a bar that can rotate about a fixed point. So a trick that you usually apply in physics, we switch the view from front view to top view. So this is the top view of the door. The rotating point is known as the pivot point, fulcrum, or even the hinge. So now we cannot see anymore the axis of rotation simply because we have switched the view from being a front view to a top view. The axis is here. And this point, which is now the point of rotation or the axis of rotation, is known as the pivot point, the fulcrum, or the hinge. To rotate the door, we know that a force should be applied. Then upon rotation, this force will produce a torque. So here, this should be corrected and should be spelled as torque. Now, whenever the force is applied to the object and the object is able to rotate, we say that the force produces a torque around the point of rotation, which is in this case the pivot point. Then we will introduce a new quantity given by the torque, which is the perpendicular component of the force multiplied by d, where torque tau is Newton meters. Why? Because the force is in newtons and this is in meters. Now here let me make a statement which is very important. This is not the first time we see a quantity identified by Newton meters. The work, which is given by F multiplied by D, also has a dimension of a Newton meter. However, it doesn't imply that if both quantities have the same unit, it means that they're the same. This is work, this is torque. F perpendicular is the perpendicular component of the force applied to the body and in newtons. Now, after a while, I'll explain how to obtain using projections the perpendicular component. Now, D is the distance from the pivot point to the point where the force is applied. Let's assume that the force represented in red is applied at this point, and this is the pivot point. Then the distance d is the distance from the pivot point to the point where the force is applied. For this reason, in this case, it is important to draw something called the rigid body diagram and not the free body diagram, as we shall see. Now, the perpendicular component of the force is determined by projecting the force along the tangential direction. So this is perfect. Now we need to identify what is meant by the tangential direction. Then tau, which is basically defined here, the perpendicular component of the force multiplied by d, is either plus minus fd cosine theta tau I, because we know that a projection is given by the cosine theta with a plus or a minus sign. Now we need to identify what is theta with respect to the tangential direction, where f is the magnitude of the applied force. So now we know what is f. F should be given in the exercise itself. D is the distance from the pivot point to the force to the point where the force is applied. Okay. Now theta is the angle between the force and the tangential direction of rotation, and let me specify the tangential direction. Now the radial direction is the direction or the line along which passes through the center of rotation. So now we know that this point is the center of rotation. If you assume this point that it will rotate along this point as if it's covering the trajectory of a circle, then that would be the radius, this imaginary line. Then we call this line to be the radial direction. The tangential direction would be an imaginary line passing or perpendicular to the radius, as we know, from a circle and passing through the point where the force is applied. Then F perpendicular So let me repeat again and identify the radial direction. The radial direction is the direction along the radius passing through the center of rotation, which is the pivot point. The tangential direction would be a direction perpendicular to the radial direction and passes through the point of application of the force. Now, F perpendicular is the projection of the force along this tangential direction, then theta would be identified by this angle. Okay, so the first thing is to identify the radial direction, tangential direction, then we can identify the angle theta, in which cosine theta would be multiplied by F and D. Now let me state clearly, the torque is a vector quantity, then it is associated with a direction and a magnitude. In order to complete the analogy between a force and a torque, then the torque should be promoted from being scalar to a vector. Now what causes this plus or minus sign? We didn't discuss it so far. An applied torque that causes a body to rotate in a counterclockwise direction is said to be positive torque. Now notice that this force will cause the door from a top view to rotate in this direction, and this is known as the counterclockwise direction. Why? Because it's opposite to the motion of the hands of the clock, and this is by default is taken to be the positive torque. Then in this case the torque is given by plus Fd cosine theta. The associated vector would be pointing out of the plane of the page. So what does this mean? Now here we have a top view which can be represented by the following plane or sheet. Then the torque would be assumed to be a vector which is perpendicular to the plane containing the bar and the top view. Now that would be difficult for us to represent this vector in a top view. So to do so, we will assume that it would be represented by a dot, and here we will place a dot. Why? Because if the vector is pointing out of the plane of the page, which is something like that, so if you're looking at the vector from this side, so you will see that the vector is being represented by a dot. So whenever the dot or whenever the vector is pointing out of the plane of the page, then it will be represented by a dot. Now, how do we know that in this case it's pointing out of the plane of the page? This is done by the right hand rule. The four fingers, so first of all you should carry your hand, and the four fingers should be rotated in the direction of this arrow. Then the thumb would be pointing out of the page. Now it's a bit challenging to do this representation in a video, so this will be covered later in class in details. Now what about a force that causes a body to rotate in the clockwise direction? So an applied torque that causes a body to rotate in a clockwise direction is said to be negative torque. So if we need to calculate the torque produced by this force, we would say that would be this force is causing the bar or the rod or the door to rotate in a clockwise direction, which means it's a negative direction. Then it's given by minus Fd cosine theta. The associated vector would be pointing into the plane of the page, which is like that down. Now it's difficult here to represent a vector which is like this, but suppose that the vector is going away from you and you're looking from this side. So you will notice that due to the shape of the arrow from the back view, as if it is a cross, which means in this top view it will be represented by cross. So this is basically the vector representation of the torque. Now we're gonna do the following application. A bar of mass 2 kg of dimension 120 centimeters is hinged from the left end free to rotate. Three forces F1, F2 and F3 are applied to the bar as shown. So the mass of the bar is 2 kg and the dimension, which means the distance from here to here, is given by 120 centimeters. Calculate the torque produced by each force. Now here apparently we have three forces acting on the rod, so we need to calculate the torque produced by these three forces. Then let's start by the force F1 in order. Then in order to calculate the torque produced by this force, first we need to identify the radial direction, then the tangential direction, then we can project the force. So that's the radial direction and that's the tangential direction. If this is the angle 30, then that's the angle 60. And the torque would be plus y plus, because this force will cause the door or the bar, so here we're talking about not a door, to rotate in this direction, so in the positive counterclockwise direction. And now we know what's the value of F1, which is 120, D is 0.8. YD here is 0.8. Let me show you the calculation. So if the bar is given by 120 centimeters and the distance, so let me do the following. If from here to here is 120 centimeters and from the right edge to this point is 40 centimeters, then 120 minus 40, that would be 80 centimeters, which means the distance D from the point of rotation, which is the pivot point as shown here, to the point where the force is applied is given by 80 centimeters. Converting it into meters, that would be 0.8. And cosine 60 would be 0.5. Then the torque tau 1 produced by the force F1 would be 48 newtons meters. Now the torque 2 would produce no torque, and this is because the line of action of F2 passes through the pivot point. Then let me explain that. Not every force causes a torque. If you think about it, if you have a bar that can only rotate either counterclockwise or clockwise, and suddenly you started applying a force toward the left, this will causes no rotation, or in other words, this will causes no torque. Why this is happening? Simply because the line of action of F2, which is directed toward the left, passes perfectly through the pivot point. So whenever the force has a line of action that passes through the pivot point directly, we can assume that the torque produced by this force is 0 because it will cause no rotation. Now, as for the torque produced by the force F3, so again, we need to identify the radial direction. Radial direction has been identified perfectly. The tangential direction would be along the force F3. So since the force F3 completely lies along the tangential direction, no need for a projection. Now it's left to determine whether it produces a negative or a positive torque. It will causes the bar to rotate in this direction, which means a negative torque. Then that would be minus F3D. I will repeat again here, there is no projection simply because F3 lies completely along the tangential direction. Now F3 is given by 150. D in this case represents the distance from the force F3 to the pivot point, which is basically 35 centimeters, which is 0.35. And plugging that on the calculator, that would give us that the torque is minus 52.5 Newton per meter. And as you can see, that the torque might be 0, might be positive, might be negative, because we have promoted the torque to be a vector quantity. However, if you look at the exercise carefully, they're telling us to calculate the torque produced by each force. We know that in such type of problems, there are apparent forces that are represented on a rigid body diagram, and there are hidden forces like the pull of gravity and the normal reaction. And then let's represent the pull of gravity. So the pull of gravity, since we're assuming a bar which has a uniform mass distribution, although it's not stated explicitly in the exercise that it has a uniform mass distribution, but we're doing this assumption, then the pull of gravity would be acting on the center of mass, which is located at the center of the object, which is 60 centimeters away from the pivot point, or 0.6 meters. Now the pull of gravity would produce a negative torque. Luckily, it lies completely along the tangential direction. Radial direction has been specified, that would be the tangential. So now it's given by minus FGD. Now the pull of gravity is given by mg, and the distance t is 0.6. Then m is 2. We will assume that g is 10 because the number seems to be perfect, and that would be minus 12 Newton meter. Then the torque produced by the pull of gravity around this pivot point is given by minus 12 Newton meter. And finally, I have stated something about the normal reaction. Although the bar, under the bar, we don't have any table or floor, however, there is not precisely a normal reaction, but a reaction on the pivot point. Now here, why we're not saying normal reaction? Because it won't be perpendicular to any specified direction. Now, such type of forces called reaction always occur whenever two bodies are in contact. And this is reasonable because whenever two bodies are in contact, there will be a force exerted by body A on body B, and there is a force exerted by body B on body A. Since we're interested in the forces exerted on the bar, then there will be a force exerted by the pivot on the bar, and this is given by the force R. Now, I have represented the vector R to be in any arbitrary or random direction simply because it will produce no torque. For the same exact reason, the line of action of R passes through the pivot point. Now, it is important to state that there is a force R exerted by the pivot on the rod, on the bar, but it produces no torque, so the line of action of R passes through the pivot point, which causes no torque. Then how many forces we have in total? We have 5 forces, 3 forces that are apparent and 2 forces that are hidden as usual, given by the pull of gravity and the reaction, not the normal reaction, because this reaction won't be perpendicular to any specified known direction through the rigid body diagram. Now in part B, they're asking us to calculate the net torque, and the net torque means total. So that would be tau 1 plus tau 2 plus tau 3 plus tau g plus tau r, and if you add the numbers, that would be negative. State the direction of rotation of the bar, since the torque is given in the negative direction, and here there is something missing in the exercise. We should assume that it starts or released from rest, because we know that torque is in analogy with force, so it means acceleration, and we know that acceleration that doesn't give us the direction of motion. So here, in order to make this exercise perfect, I should write the following statement. The bar is initially at rest. Okay. Now in this case, indeed, since the torque is negative, then the bar will rotate clockwise in the negative direction. Clockwise means in this direction. And now for the rest of the video, we're gonna solve exercises, the MCQ. Then let me start by exercise 1. A meter stick of negligible mass is placed on a fulcrum at the 0.4 meter mark. So here we have the following bar. Okay. Sorry, the meter stick. By meter stick, it means that the length of this stick is 1 meter. So this is the left edge, this is the right edge. The fulcrum, which is the point of rotation or the pivot point, is placed at the 0.4 marks. So this is 0.4 marks. If this is 1 meter stick, then that would be 0.6 marks. With the 1 kg mass hung at the 0 mark, so this is the 0, this is the 1 meter mark. We're measuring from left to right. Here we have 1 kg, and here, and the 0.5 kg mass hung at the 1 meter mark. So here we have a 0.5 kg. The meter stick is held horizontal and released. So released from rest. Immediately after release, the magnitude of the net torque on the meter stick about the fulcrum is most nearly. So we need to find the torque produced by each force. Then we will calculate the net torque. So how many forces do we have here? First of all, we have 2 apparent forces given by the force exerted by the 1 kg on the meter stick. So let me erase this, and here we will say I will have a force given by F1. If the mass is given by 1 kg, then 1 multiplied by 10, that would be 10 newtons. Then we have a downward force of 10 newtons here. And here similarly, we have a downward force given by F2, which is 0.5 times 10, which is 5 newtons. Now these are the 2 apparent forces. What about the hidden forces, like the pull of gravity and the reaction force? We don't have the pull of gravity simply because the meter stick is of negligible mass. So I won't represent the pull of gravity. And here, somewhere at this point, in a random direction, we have the reaction R that will produce no torque. So basically the net torque would be the torque of this force plus the torque of this force plus this one, which is 0. Then the torque 1 produced by the force F1, then this is the radial direction. Now F1, which is vertical down, acts along the tangential direction. It will produce torque in this direction, which is the positive direction, then plus F1 multiplied by the distance d, which is 10 multiplied by 0.4, and that would be 4 Newton meter. Now what about the torque tau 2? Tau 2 will produce a torque in this direction, which is negative. Now similarly, it lies completely along the tangential direction, so no need for a projection. That would be F2 multiplied by d, then minus 5 multiplied by 0.6, and that would give us a value of minus 3 Newton meter. Now the torque tau r would be 0. If this is a free response, you should justify that the line of action of r passes through the pivot point, and the net torque would be the sum of all of these torques, which is 4 minus 3 plus 0, and that would be 1 Newton meter, which makes A to be the correct answer. Now, exercise 2. In order to model the motion of an extinct ape, scientists measure its hand and arm bones from shoulders to wrist. The arm bones are 0.6 meters long and their mass is 4 kg. From wrist to the tip of the fingers, the hand bones are 0.1 meters long and their mass is 1 kg. In the model above, each bone is measured to have uniform density, which means that the center of mass is located geometrically. This is the shoulder here. That's the shoulder. The arm is held in the horizontal position and the hand is bent. So let me remove this as well. And the hand is bent at the wrist so that the fingers point up as shown in the figure above. The torque exerted by the weight of the hand with respect to the shoulder is most nearly. So with respect to the shoulder, which means that the pivot point is here, we're talking about the weight of the hand. The weight of the hand is the pull of gravity, which is directed downward like that. So that would be the pull of gravity of the hand, which is given by mg. The mass is 1, g is 10, so that would be 10 newtons. They're only interested in the torque exerted by the weight of the hand, not by all the forces. Then how can we determine the torque? So we need also, let me first, okay. Now this will cause rotation in the following direction, which is it's negative. The force times the distance d. The force is given by 10. Now here no need for a projection because it's completely along the tangential direction. This is the radial. Now the distance t would be 0.6 and that would be minus 6 Newton meters, since all of the answers are positive, which means A would be the correct answer. And finally, exercise 3, a student will hold the left end of 5 identical meter sticks. Each meter stick has a weight or weights attached to it as shown in the figure below, in which case the torque about the student's hands to be greatest. Now the torque is given by Fd and it's affected by two factors. By the force Nd. As the force increases, the torque increases. As the distance increases, the torque increases as well. Now it's not reasonable to calculate the torque produced by each mass, so let's start eliminating. If A and B have the same, so the pivot point, so let me assume that the student hand is here from the left, so the pivot point is assumed to be the same for all three configurations. Now in this case, the torque produced by 300 grams is greater than 250 grams, so that would be greater, then we can directly eliminate this. Now we can directly eliminate B because between C and C is greater than B because it has an additional mass which will produce more torque. Now we can eliminate directly D because E compared to D, E, the 500 grams is located at a greater distance and a greater mass, so now it's left then to calculate the torque produced by configuration E and configuration C. For configuration E, now I will ignore the minus sign, although they are producing torque in the negative direction since we're only interested in values. The mass here is 500 grams, which is 0.5 kg, and that would exert a force of 5 newtons. Now here, if this is a meter stick, then we can say that would be, say for example, okay, we can assume this is to be 1, 2, 3, 4, 5, 6, 7, 8. Now, if I want to be precise, I should say that this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, but that won't change anything. Alright. So the torque in this case would be 5 times 8, let's suppose, which is 40 Newton meter. And in this case, we need to calculate the torque produced due to two forces. That would be 0.25 kg, which is 2.5 newtons. Then we have 2.5 newtons multiplied by 1, 2, 3, 4, 5 plus 2.5 newtons multiplied by 10, which is the length of the meter. And if you plug that on the calculator, that would give you 37.5 Newton meter, which means that the torque produced by the 500 grams at this specific location is greater than the torque produced by the two masses combined at these specified locations, then E would be the correct answer. Then that's it for me in this video, guys. See you soon and a new one.